Okay, so let's start up with even and odd functions. A function is called an even function. This is still 1.5, by the way. If f of x is equal to f of negative x. The graph of an even function is symmetric about the vertical axis. We also have odd functions. A function is called an odd function if f of let me rephrase this one. If f of negative x is equal to negative f of x, another way of phrasing this is if f of x is the same thing as negative f of negative x. In other words, if I reflect this function across both axes, I get the original function. So these are both valid definitions because they're really saying the same thing, right? We see if we multiply both sides by -1 in this first one, I actually get the second one, right? The graph of an odd function is symmetric about the origin. Now, a function can be neither even nor odd if it doesn't exhibit symmetry. For instance, f of x equals 2 to the x power is neither. This is just an example. It's not the only one that's neither even nor odd. But there are functions that are neither even nor odd out there. Let's look at an example. Is the function f of x equals x cubed plus 2x even, odd, or neither? Without even looking at the graph, we can determine this by plugging in negative x for x here. If I substitute in negative x, I'll be able to see is f of x or is f of negative x equal to f of x? If so, the function is even. Is f of negative x equal to negative f of x? If so, the function is odd. And if it doesn't meet either of those qualifications, then it's neither. So f of negative x is negative x cubed plus 2 times negative x. This is negative x cubed, that's negative x cubed, plus 2 times negative x, this is minus 2x. Notice that I can factor a negative sign out of both of those to get minus x cubed plus 2x, because I have to factor this negative sign out of both if I factor out a negative. And this is just minus f of x, right? Because f of x was x cubed plus 2x. So since f of negative x equals negative f of x, this means that this function is odd. Notice that this also means that with an odd function, performing a horizontal reflection is the same thing as performing a vertical reflection. Let's look at stretches and compressions. So we're going to have a similar definition. These are all going to be similarly worded, right? So this is a new topic, by the way. This is not related to the even odd. This is not related to the even and odd stuff. So this is a new topic. Although this is relevant to transformations. So given a function f of x, if we define a new function g of x as g of x equals k times f of x, where k is constant, then g of x is a vertical stretch or compression of the function f of x. If k is greater than 1, the graph will be stretched. If k is between 0 and 1, let me make sure this is very clearly a k, since I have less thans here, the graph will be compressed. And if k is less than 0, there will be a combination of a vertical stretch or compression with a vertical reflection. Let's look at an example in a graph here. In this graph, this is a transformation of the function f of x equals x cubed. That's one of our toolkit functions, as they're called. This is a stretch or a compression of x cubed. In order to determine what's going on here, let's find a point on this graph. I see 0, 0, but 0 isn't going to be helpful for me for reasons that'll be made clear in a second once we start working this out. It looks like this passes through the point 2, 2. And it does pass through the point 2, 2. So that's good. So, let's see, 2, 2. Okay. I'm going to minimize this. And because I know that this is a transformation of x cubed, I know I have the point 2, 2 on this new graph. Then I know that this g of x, whatever it is, has to be some number k times f of x. So I know that my g of x has to be some number k times x cubed, since here I have f of x equals x cubed. Now I can plug in my x value and my y value. I can plug in my x value for x, I can plug in my y value for g of x, and I can actually solve for k. Notice that the point 0, 0 doesn't do us any good here, because if I plug 0 in for x, then I get k times 0, which is 0, and that doesn't let me solve for k. So I needed one of these points that didn't have an x value of 0. So I'm plugging 2 in for g of x because I had a y value of 2 at this point. I'm plugging 2 in for x because I had an x value of 2 at this point. This gives me 2 equals 2 cubed is 8, so this is 8k. If I divide both sides by 8, I get that k here is 1/4. And so the graph we looked at was the graph of g of x equals 1/4 x cubed. Now let's get some definitions for horizontal stretches and compressions. Given a function f of x, if we define a new function g of x, as g of x equals f of k times x, where k is a constant, then g of x is a horizontal stretch or compression of the function f of x. If k is greater than 1, graph will be compressed by a factor of 1 over k. If k is between 0 and 1, the graph will be stretched by a factor of 1 over k. And if k is less than 0, there's a combination of horizontal stretch and of a horizontal stretch or compression with a horizontal reflection. All right, and last up, let's go over some rules for combining transformations. Combining vertical transformations is easy, or simple, simpler than the horizontal ones at least. When combining vertical transformations, written in the form a times f of x plus k, first vertically stretch by a, then vertically shift by k. Combining horizontal transformations is slightly different. When combining horizontal transformations, written in the form f of b times, this is not b of, this is b times, oh wait, no, I'm looking at the wrong one, sorry. When written in the form f of bx plus p. First, we horizontally shift by p. Then horizontally stretch by 1 over b. This ends up being a bit difficult though, because it's usually easier to horizontally stretch a graph before shifting. So if I factor the inside of my function, this can be a little bit simpler. So alternatively, if I have factored them, if I'm combining horizontal transformations written in the form instead f of b times x plus p divided by b, this is just what I get whenever I factor a b out of this definition here, right? In this case, I first horizontally stretch. So all of the first words being the same here. By a factor of 1 over b, then horizontally shift by this number p over b. This is just going to be one number, of course, but and the last note that we have to make about these transformations is that horizontal and vertical transformations are independent This means that it doesn't matter whether horizontal or vertical transformations are done first. You can do the vertical transformations and then do the horizontal transformations, or you can do the horizontal transformations and then do the vertical transformations. It doesn't matter. And that's it for 1.5.